Okay, this is going to be the first in a series of videos about particle accelerators. So we can think of this as the introduction. And we're going to do these videos as a history of particle accelerators, and so this will be the early history, and we'll go on to talk about how this has developed and where we now are with particle accelerators and their use in physics. So particle accelerators have a wide range of uses in physics. They are used in industry, in medicine, and in research. I think the public imagination with regard to particle accelerators is grabbed more with the research side. Many people have heard of the Large Hadron Collider in Switzerland, which has a circumference of 27 kilometres and straddles the Swiss-French border. It's massive. It's the most expensive experiment that has ever been built to date. But particle accelerators can be really small. They can fit onto workstations and in laboratories, and they have a wide range of uses. So what is a particle accelerator? Particle accelerators are used to make particles go faster, essentially. Sometimes we wish to collide these particles. So in some of the bigger particle accelerators, you'll get them going really fast, and you'll collide these particles together, and then you'll analyze what is created in the aftermath of these collisions. And that's how physicists discover new particles. That's how they have been able to probe the inner workings of the atom and what matter is made of through these experiments. One of the problems with these types of experiments is you're wanting them to go very fast, and that requires huge amounts of energy. Some particle accelerators actually have power stations next to them because the energy requirements are so massive. Now, up till now, when we've talked about energy, we've talked about it being measured in joules. But joules is a really big unit of measurement. 1 joule of energy is quite a lot of energy. And when you're talking about these tiny little subatomic particles, we don't use joules, we use electron volts as our way of measuring how much energy these particles have. And we call it the unit would be EV, electron volts. 1 electron volt is the same as 1.6 times 10 to the minus 19 joules, which, if you are remembering, that is the same as the charge on an electron. The energies that we get these particles up to can be many thousands or millions of electron volts. The unit gives us a better indication of the energy transferred when we say 40,000 electron volts going to 60,000 electron volts, for example. The amount of energy that we transfer to particles, the energy transfer depends on a number of factors. For example, the type of particle. these could be ions, electrons, protons, etc. And they all have different charges and they have different masses. The speed we require to accelerate to. And also the purpose of the experiment. Now, at this most fundamental level, fundamentally, a battery is a simple particle accelerator. Think about it, we've got, these are our electric plates of our battery, and we have one plate at 0 and we've got this potential difference, and this is at some positive number of volts, and we have our electron and we're accelerating it across this gap between our two plates and through our, across our electric field. The electric force of the field is what accelerates the electron, giving it more energy. The purpose of a battery is to power a circuit, while more sophisticated particle accelerators are used to generate radiation or radioactive samples or to investigate subatomic particles. So let's think about some of the earliest particle accelerators. So in 1870, there was a man called William Crooks. Designed a cathode ray tube, and I will bring it up. This this is one of the most earliest forms of particle accelerator. It was based on the Geissler tube. And it's small glass tubes that contain a gas. You can see each one has a slightly different colour. It'll depend on the kind of gas that is inside the tube. A large potential difference, you'd have, wait a minute, let's get rid of this here. So this is the Geissler tube. So what you would do is, I will try and get a different colour that will show up on the black. So you would have a potential difference. That's not going to work. Never mind. So we've got a potential difference here. Just like what you'd have with a battery. It's applied across the tube, and the current causes the gas to glow. This phenomenon occurs as a result of the fast-moving electrons. So you've got electrons that are being accelerated through the tube across the potential difference, and as they collide with the gas particles, so if you think about, we've got our potential difference and you've got our electrons whizzing through here, and they collide with a gas atom. And what these collisions cause is within, so here's your nucleus, and you've got the electrons going round your gas atom. And as they collide with these atoms, the electrons, these are in different energy levels. And say if in the atom, the gas atom here, not the electron, the gas atom in here, the electrons are in different distinct energy levels. If you've done any chemistry, you will see that these, when the electron hits them, they can cause this electron to drop down to a lower energy level, and when it drops down, it emits a photon of light. So when these, you have the potential difference, the electrons passing through them, they're colliding with these gas atoms, and they're causing this emission of light from the gas atoms as they interact with, as the electrons interact with the gas atoms. What then Crook did was he developed this idea further, and he came up with a more sophisticated model. Now I've got a picture of that one, I'll bring it up. So this is Crook's more sophisticated version of the Geissler tubes, and it was called the Crooks tubes. So what Crookes did was he created a lower pressure vacuum in the tubes, which meant that, so this, therefore the electrons could travel faster. So in our Geissler tubes, when the electrons, the potential difference was applied, the electrons went through the tube, they were colliding with the gas molecules and causing this emission of light, which caused the tubes to glow. In the Crookes tubes, Crookes sucks out the air, so there's very little gas or no gas in here, so he's created a vacuum, but he's still got these tubes at a potential difference. So the electrons go from one side to the other, just like they would over the potential difference in a battery. And as they do it, because there's no gas in there now, they're not got anything to slow them down. So if you think about in the Geissler tubes, when the electrons were travelling across the potential difference, as they collide with the gas, they're slowed down. But in the Crookes tubes, that doesn't happen. So they can travel further and they can travel faster, so that they can get to a higher acceleration. Crookes refined this experiment, and he was able to get to a stage where there was a stream of electrons in this cathode. So you get this. So what he managed to do was get his tube, and as he refined it, he managed to get this stream of electrons. So this is a cathode ray. When it strikes this far end, it causes a phosphorescence. I can't say that word. Another kind of light glowing emission. And that's what you're seeing in this picture. This phosphorescence. Oh, I can't say it. Of light. Now, later on, in 1895, so Crookes was doing his experiments in the 1870s. In 1895, another William, this time Wilhelm, must have been German, Rontgen, he was studying Crookes tubes, and he noticed something peculiar. He used photographic plates nearby, so they're not touching. He didn't have them touching the Crookes tubes, he just had them sitting nearby in his laboratory, and he noticed they became clouded. He deduced that there must be something being emitted from the tubes, some kind of radiation was being generated and emitted from these tubes that caused the photographic paper to become clouded. In the same way, if you were to get, in the days before digital photography, when you were developing a photograph, you would have to take this photographic paper and you would take the negatives that you'd from the film of the camera, and you would shine a light through it to create an image on the photographic plate, and then the different lights, shades of light and dark, would cause the development of this image on the photographic paper, because the paper was photosensitive. It would change with light. Light being electromagnetic radiation, if you take photographic paper and expose it to other types of electromagnetic radiation, you will see this clouding effect. So Rontgen deduced that these Crookes tubes must be emitting some kind of electromagnetic radiation. These emissions were shown to be X-rays. Rontgen was the first to discover X-rays, and for his work he won the Nobel Prize in 1901. And it's actually an adapted version of Crookes tubes that are still used today for the production of X-rays that we use in medicine. Around the same time, there was an English physicist called J.J. Thompson. And he was a physicist working at Manchester University, and he was also working on cathode ray tubes. He realised that he could change the direction of the cathode ray by using a magnet. So he had his cathode ray tube, and there's his cathode rays, and he took his cathode ray, and what he did was he put a magnet here. Well, this is not very sophisticated. You get the idea. And what he discovered was it caused the ray to bend. And so from this, he deduced that the ray must be negatively charged particles. And what he discovered was that they must be also much smaller than what had been considered possible in the size of subatomic particles. He realised that they must be part of the atom, and he called them corpuscle. This is what we now know as an electron. For this discovery, J.J. Thompson was awarded the Nobel Prize in 1906. And you could argue this is the first time that a particle accelerator was used to discover a subatomic particle. Now, after this time, in the 1930s, we have two physicists, and they were doing experiments with evacuated tubes. So you had John Cockcroft and you had Ernest Walton, and they built a special generator. They built a generator that was able to produce, so it produced 800 kilovolts of DC current, but it produced it from 200 kilovolts of AC supply. This potential was able to accelerate protons towards a lithium target. So this is what it would look like. This is what they built. This is known as the Cockcroft Walton generator. And it's sometimes you'll hear it called the Cockcroft Walton multiplier. And its circuit diagram looks like this. This is a very important circuit diagram in the world of particle accelerators and particle physics. So this was the first time they were able to take an AC supply and then turn it into a DC supply in this way. And when they did this, they were able to accelerate protons to a lithium target. So you have your protons, and they accelerated them to a lithium target. And what this did was it caused nuclear transmutation. Now, nuclear transmutation is when you change a chemical element or an isotope, and it's changed into another element or a different isotope. So you're actually able to change either the number of protons or the number of neutrons with an atomic level within the sample. That's nuclear transmutation, and this was the first time this was done, and for this they won the Nobel Prize. Today, Cockcroft Walton generators are still used in particle accelerators to help to accelerate the particles to the speeds in which they need to be in. So this was a huge breakthrough in the study of particle accelerators and the development of particle accelerators, and opened the door for more powerful accelerators to be built. In the next video we'll look more into this. We'll look at linear accelerators and cyclotrons and how this developed new areas of physics.